Dear students, welcome to the 8th unit of Software Engineering. In Unit 7, you were introduced to data design, architectural design, analysis of different architectural designs, mapping requirements into software architecture, and refining the architectural design. In this unit, you will learn software testing concepts, objectives of testing, principles of testing, test case design, and different techniques for testing. Objectives of this unit are to develop an understanding of software testing fundamentals, to understand objective of software testing, to understand testing principles, to learn to develop test case designs, to understand different techniques for software testing. Let's start our discussion from Software Testing Fundamentals. Software engineer develops a product based upon the concepts he has developed after customer communication and observation of the existing system. After a software product is developed, it is tested before delivering to the customer. In order to test a software product, software engineer develops test cases. During testing, the system is manipulated by giving different types of input and checking whether the tests can diagnose all types of errors. Moreover, it is checked whether the system is properly functioning and providing accurate results. It is also ensured that different parts of the system are properly integrated. Thus, we can say that the objectives of testing are to find errors in the software developed. Testing should be done in such a way that it reveals undiscovered errors in a minimum amount of time. To check that working of the software functions is according to the specifications. Their behavior and performance requirements are being fulfilled. To check the reliability and quality of software. Now we will discuss testing principles. Before developing test cases, a software engineer must understand the testing principles. Some important testing principles are: tests should be designed in such a way that they identify errors in the system related to customer requirements. Test planning should begin as soon as the requirements model is complete. Detailed definition of test cases can be made after the design model is complete. Experience shows that errors are repetitive. Generally, if 20% of the program module is properly checked, then 80% of the errors are identified which repeat throughout the program. Testing should be applied to individual components first, then to integrated clusters of components, and finally to the entire system. Program logic should be properly checked, and it should be ensured that all conditions in the component level design have been exercised. To be most effective, testing may be conducted by an independent third party that is competent and is unaware of the development stages. An important concept related to testing is testability. Testability is the measure of ease of testing of a program. Certain metrics can be used to measure testability in most of its aspects. Sometimes testability is also used to mean how adequately a particular set of tests will cover the product. In general, testability determines if the system is operating properly, controllable, decomposable, simple, stable, and understandable. A good test must possess these characteristics. Number 1. A good test has a high probability of finding an error. To achieve this goal, the tester must understand the software and attempt to develop a mental picture of how the software might fail. For instance, in personal information system, to check name field, the tester can give values in negative numbers or values having decimal numbers, etc., and check whether the system works properly or not. Number 2. Every test should have a different purpose because testing time and resources are limited. Number 3. A good test should have the highest likelihood of uncovering a whole class of errors. Number 4. A good test should be neither too simple nor too complex. Related to testing is testability. Testability is the measure of ease of testing of a program. Certain metrics can be used to measure testability in most of its aspects. Sometimes testability is also used to mean how adequately a particular set of tests will cover the product. In general, testability determines if the system is operating properly, controllable, decomposable, simple, stable, and understandable. A good test must possess these characteristics. Number 1. A good test has a high probability of finding an error. To achieve this goal, the tester must understand the software and attempt to develop a mental picture of how the software might fail. For instance, in personal information system, to check name field, the tester can give values in negative numbers or values having decimal numbers, etc., and check whether the system works properly or not. Number 2. Every test should have a different purpose because testing time and resources are limited. Number 3. A good test should have the highest likelihood of uncovering a whole class of errors. Number 4. A good test should be neither too simple nor too complex. Test case design. Test case design is an important activity in software engineering and should be done very carefully so that a test case should be complete and it must possess the highest probability of finding errors with a minimum amount of time and effort. There are different methods to develop a test case. These methods provide the developer with a systematic approach to testing. These methods also provide a mechanism that can help to ensure the completeness of tests and provide the highest likelihood of uncovering errors in software. Any software can be tested in one of two ways. Number 1. Knowing the specified function that a product has been designed to perform, tests can be conducted that demonstrate each function is fully operational while at the same time searching for errors in each function. Number 2. Knowing the internal workings of a product, tests can be conducted to ensure that internal operations are performed according to specifications and all internal components have been adequately exercised. The first test approach is called black box testing and the second white box testing. Since white box testing requires exhaustive testing, therefore mostly white box testing is preferred. Let's discuss these types of methodologies in detail. Black box testing is to test the functionality of the system. For example, when black box testing is applied to software engineering, the tester would only know the valid inputs and what the expected outputs should be, but not how the program actually arrives at those outputs. It is because of this that black box testing can be considered testing with respect to the specifications. No other knowledge of the program is necessary. Black box testing focuses on the functional requirements of the software. That is, black box testing enables an important basis path testing is a white box testing technique first proposed by Tom McCabe. The basis path method enables the test case designer to derive a logical complexity measure of a procedural design and use this measure as a guide for defining a basis set of execution paths. Test cases derived based on basis path technique execute every statement in the program at least once. To understand basis path testing, we must have an idea of flow graph notation, cyclomatic complexity, graph matrices, and derivation of test cases. Number 1. Flow graph notation. Flow graph is a graphical way to represent logical control flow using the notations as shown in figure. On a flow graph, arrows called edges represent flow of control. Circles called nodes represent one or more actions. Areas bounded by edges and nodes are called regions. A predicate node is a node containing a condition. In addition to this, a flowchart is used to depict program control structure, and the figure shown is mapping the flowchart into a corresponding flow graph with the assumption that no compound conditions are contained in the decision diamonds of the flowchart. In this figure, each circle called a flow graph node represents one or more procedural statements. We can map a sequence of process boxes and decision diamonds into a single node. An edge must terminate at a node even if the node does not represent any procedural statements. Dear learners, let's discuss cyclomatic complexity. The cyclomatic complexity gives a quantitative measure of the logical complexity. This value gives the number of independent paths in the basis set and maximum number of tests to ensure that each path is executed at least once. An independent path is any path through a program that introduces at least one new set of processing statements or a new condition, that is, a new edge. Example shown has cyclomatic complexity of 4, which can be calculated by any of the three methods discussed here. Number 1. Count number of regions of flow graph. Since there are 4 regions in this flow graph, therefore cyclomatic complexity is equal to 4. Number 2. Count the number of edges, subtract number of nodes from it, and add 2 in it. Here number of edges are 11, number of nodes are 9. 11 minus 9 becomes equal to 2. Adding 2 in it counts 4, so cyclomatic complexity is 4. Number 3. Count the number of predicate nodes, add 1 in it. Here predicate nodes are 3, add 1 to it, cyclomatic complexity is 4. Cyclomatic complexity tells us that there are 4 independent paths in this flowchart. These independent paths are shown on the screen. Cyclomatic complexity provides upper bound for number of tests required to guarantee coverage of all program statements. Dear learners, before deriving test cases, consider a procedure described by Pressman in his book of software engineering. The procedure computes the average of 100 or fewer numbers that lie between a range or boundary values specified by user. The procedure should compute the sum and count all the numbers that fall in the given range. These numbers will be called valid numbers. Number 1. Using the design or code as a foundation, draw a corresponding flow graph. A flow graph is created according to PDL statements in the program. Different symbols and construction rules are used to draw a flow graph. For the procedure described above, flow graph developed is as shown in figure. Number 2. Determine the cyclomatic complexity of the resultant flow graph. The cyclomatic complexity can be determined by using the formulas. We can also determine cyclomatic complexity without developing a flow graph. For this purpose, we count all conditional statements in the program logic and add 1. For the procedure, average cyclomatic complexity can be determined as cyclomatic complexity is equal to 6 regions. Cyclomatic complexity is equal to 17 edges minus 13 nodes plus 2 is equal to 6. cyclomatic complexity is equal to 5 predicate nodes plus 1 is equal to 6. Number 3. Determine a basis set of linearly independent paths. Linearly independent paths through the program control structure can be determined through cyclomatic complexity. Therefore, 6 paths are identified for this procedure. Path 1 would comprise of nodes 1, 2, 10, 11, 13. Similarly, other paths would be as shown on screen. Number 4. Prepare test cases that will force execution of each path in the basis set. Test cases should be designed in such a way that each path in the program is tested after execution. For the procedure, average test cases designed are: consider path 1. Test case for it would be to check that the input given is valid or not. Here, valid input is denoted by value of k. Input would be valid if it is less than I. Since we have written procedure to compute 100 or less number of values and I is initialized from 1, so valid input would be greater than or equal to 2 and less than or equal to 100. We have also specified minus 999 as a valid input to terminate the program. We have denoted it by value of I is equal to minus 999. Expected results are the correct average based on valid input values and proper totals. An important thing to note here is that path 1 cannot be tested standalone but must be tested as part of path 4, 5 and 6 tests. Now consider path 2. Here we have to check the program by giving the input value minus 999. If it gives the average value minus 999 and terminates, then the program is working properly. Expected result is the average equal to minus 999. Let's consider path 3 now. Test case for this path would be to attempt to process 101 or more values. First 100 values should be valid. Expected results are the correct average based on valid input values and proper totals. It would not process any value of I which is greater than 100. Dear students, now we will learn other test methods. One such method is to prepare a graph matrix. A graph matrix is the tabular representation of a flow graph. It can help to evaluate program control structure during testing. In a graph matrix, number of sides is equal to the number of nodes on the flow graph. Rows and columns correspond to the nodes. Entries correspond to the edges. In the figure, each node on the flow graph is identified by numbers, while each edge is identified by letters. a letter entry is made in the matrix to correspond to a connection between two nodes. For example, node 3 is connected to node 4 by edge B. We can also show link weights in the matrix appearing on the screen. In this matrix, the link weight 1 shows that a connection exists and 0 shows that a connection does not exist. Represented in this form, the graph matrix is called a connection matrix. Each row with 2 or more entries represents a predicate node. Use a value of 1 to calculate the cyclomatic complexity. For each row, sum column values and subtract 1. Sum these totals and add 1. Control structure testing. Control structure testing is a group of white box testing methods. It includes condition testing, data flow testing, and loop testing. Condition testing focuses on exercising the logical conditions in a program module. Errors in condition can be due to Boolean operator error is due to misuse of AND, OR, and NOT operators. For example, instead of using AND, you use OR operator, the result would be different. Boolean variable error can be due to incorrect usage of any Boolean variable. For example, we want to write B1 or B3, but we write B2 or B3. Here, B2 is incorrect. The result would change due to wrong use of Boolean variable. Boolean parentheses error. For example, we want to write the expression shown on the screen where first OR operator is checked and then AND operator is checked. The situation would be different if we write the expression like this. The expression would be as appearing on screen, but if we write it as shown, it would be incorrect. Relational operator error. This may be due to incorrect use of the operators less than equal to, not equal to, greater than equal to. Arithmetic expression error. For example, we want to add two values and then multiply the result with a third value. Our expression should be variable number 1 plus variable number 2 followed by parentheses and then multiplied with variable number 3. If we write this expression without parentheses, then the result would be different.